right, hey you guys. As promised, I wanted to go over some notes from the worksheet. I think it's worksheet 3 that I put up online earlier today. So I want to just basically go over a problem with you, maybe two problems, just kind of give you an idea how to do these problems. Really, there's not a whole lot new here. Everything that we're going to do on a problem like this, you guys have done before. It's just we're kind of putting things together, just adding a few things here and there. Really, it's using Newton's second law, but we're going to throw some angles in there, which means we do have to do a little bit of trig. So again, make sure your calculators are in degrees, not in radians. Just be careful of that because obviously you don't want to get the wrong answer because of that. So really what's going to happen, this is kind of my first time doing this with the board here, so I'm going to try to make sure I stay out of the way of the camera or whatever. So I'm going to come over here, and I should have moved my chair. I should have a chair on both sides, but that's okay. So let's say we have a problem where kind of like the first problem on the worksheet looks something like this, where we have just a box on a ramp. So we're pretty used to a problem like that already. So I'm going to use some numbers I know off the top of my head. So like a 30-degree angle. Let's say maybe this particular box is 5 kilograms. And maybe I was looking for the acceleration down the ramp. Then of course you can throw something else in there. You can say something like, hey, how fast is it going at the bottom if the ramp is 5 meters long, or some of those other kinematic problems. But I'm not so concerned about that right now. Right now I just want to get you guys to the point where you guys can see a problem like this and just know how to get to that acceleration piece. So the first thing, just like every other time, you're always going to want to draw your free body diagram. So I'm going to start that. So free body diagram, you always start, you guys know this by now, that the first part of your free body diagram is we're just going to draw a dot. Now I have a small board here, so a lot of stuff I have to do is going to have to be a little bit smaller, but I think you guys will be okay. You guys can zoom in if you need to or whatever. So our first force, of course, is just going to be our force of gravity. So I'm going to write that, and I'm going to label that Fg, and then we just have to remember, so it's 5 kilograms. Remember, just multiply that by acceleration of gravity. So 5 kilograms times 10, that's going to give us 50 newtons. So I'm just going to write that there. And then my next piece, I have my normal force. Remember, normal force isn't always opposite gravity, it's perpendicular to the surface. So remember, normal force is just going to come up that direction. So I'm going to draw my normal force just up that way, and I'll just label that, of course, Fn. I don't know the value of my normal force right now, so we'll deal with that in just a few minutes. Now, that's it. Unless there's friction here, if there was friction here, of course I'd have a frictional force just going up that direction, but I'm going to treat this as if there's no friction, and we're just going to use just our Fg and our Fn, and we'll be able to show where the acceleration comes from. So our next step, of course, we're going to draw our axis in, and like I've said before, you're always going to want your axis so that the direction that the box goes, so the direction the box would go would be straight down like that, so parallel to the ramp. So we're going to draw our axis that direction. So my axis just comes straight down just like that. That's my x-axis, which means that my y-axis, of course, goes straight through my Fn. So there's my y right there. And then that allows us to draw our components in. So we're used to doing that, hopefully. I know it's actually been a couple weeks, but hopefully you guys can, remember how this kind of works. So we can just draw this part right here. That's going to be my FGY. And then right here, I have my FGX. And then this is where we just have to remember our trig. We can look at that and go, okay, well, I need to be able to figure out my FGX. I can figure out my FGY. This part right here makes a right triangle. So since that makes a right triangle, we can go through and we can figure out, knowing that my hypotenuse is 50 newtons, I can use sine, cosine, tangent to figure out my FGY and my FGX. So my angle is this angle right here. Now, that's always been a really tricky point. A lot of you guys ask me during class, how do I figure out that angle? How do I know it's there and not there? You got to kind of like go through and figure it out. What I've always said, remember, if my x-axis was right here, and then it rotated 30 degrees this way, so my x-axis was here, my normal x-axis, my left and right x-axis, went from there 30 degrees that way, which means your y-axis has to do the same exact thing. If my x-axis rotated clockwise 30 degrees, my y-axis, which was right there, had to rotate clockwise 30 degrees. So if it rotated 30 degrees, that shows you that this angle right here is going to be my 30-degree angle. I think hopefully with a little bit of practice, you guys will get used to that. Hopefully you guys already are, you know. So now at this point, you can go through and you can figure out your FGX and your FGY. Now, for this particular problem, we're looking for acceleration. So we don't even need to find our y component, because we know our y component cancels out our normal force. So we don't have to go through and solve that. You can if you want to. You just go through and figure out, okay, well, that's a cosine side, and use 50 cos 30, and you end up with your FGY. But you don't have to do that for this particular problem. Right now, what we're looking at is this force right here. And that's the force that's not balanced anywhere. That FGX didn't balance out. If it wasn't moving, or if it was at constant velocity, it's because there would be a frictional force that balanced it out, but that's not the case here. So what we have is we have our FGX not being balanced out, and there's nothing else acting in the x direction. So in this particular case, our sum of the forces is equal to our FGX. So of course we need to figure out our FGX. So again, we're looking at this particular triangle. Remember your trig rules. You can look at that and say, okay, that's an opposite side. So I'm going to go through here and I'm just going to write out, so sine 30 equals my opposite, which is my FGX, over my hypotenuse, which is my FG. So that ends up being 50 newtons. So if I go through and just calculate that, just do your basic algebra, 50 moves over here, 50 times sine 30, we end up with an FGX. In this case, 50 sine 30 is 0.5. So that gives me a 25 Newton force. So if my FGX is 25 newtons, and I'm going to use Newton's second law, then I'm just going to plug that in. My net force is just my FGX, which is here. I just solved for it. That's 25 newtons. So I'm going to go ahead and plug that in, because that's my net force, like I said. So this value right here, which is my net force, and I'm going to plug that in right there. And then my mass, we have that from our problem. Mass is right there, so we take our 5 kilograms. 5 kilograms is right here, and there's our A. And then we can just solve for our acceleration. And 25 divided by 5, that's just going to give us an acceleration of 5 meters per second squared. And we're good to go. Now again, if we have something else that's added to the problem, like I could have added anything. I could have said, hey, here we go, how long does it take for this to hit the bottom of the ramp if this is 10 meters? We just use a kinematic formula and we figure out that time. Or I could have went on and said, what's the normal force? If I wanted to figure out the normal force, then I go through and I do FGY, figure out what that component is, which is just, in that case, you would just do 50 cos 30, which is like 43.3 or something like that. And then we'd know, okay, well, Fn is going to be 43.3 newtons, But we can solve, anything at that point once we end up with our acceleration. I just didn't, I didn't ask a different question in that particular case. So that's a problem with the box on an incline. I'm going to make another video. I'll do a problem with, just another, just basic angle type problem and post that one up as well. All right, take care, you guys.